What's up guys, this is Masi. Welcome to my channel. In this video I want to talk about percent dissociation. So as you remember, we classified acids into strong acids and weak acids. Strong acids dissociated completely 100% into its ions. So we have one-way reaction, but weak acids we are dealing with a reversible reaction because only some part of the original acid dissociates into its ions, but most of them, more than 90% of them, usually remains unreacted. So that's why we need to define percent dissociation to find out what percentage of its original acid dissociate into its ions. It is often useful to specify the amount of weak acid that has dissociated in achieving equilibrium in an aqueous solution. The percent dissociation is defined as follows: amount dissociated in terms of mole per liter divided by initial concentration. So the concentration of the dissociated ion divided by initial concentration multiplied by 100%. Let's see some example. We need to calculate dissociation or percent dissociation of two acids, 1 mole per liter HC2H3O2 and 0.1 mole per liter HC2H3O2, and we have the dissociation constant of acetic acid, which is 1.8 times 10 to the power of -5. So since acetic acid is a weak acid, the major species in this solution are acetic acid and water. Both species are weak acids, but acetic acid is much stronger acid comparing to water. Thus, dominant equilibrium will be acetic acid gives us proton plus C2H3O2 minus, which is called acetate. So 1.8 times 10 to the power of -5 equals to proton concentration times acetate concentration divided by concentration of acetic acid at equilibrium concentration. So if I have the ice table, we have 1 initial concentration of acetic acid, change is going to be -x, and equilibrium would be 1 minus x. For proton, initially we have almost 0, change plus x, equilibrium is going to be 0 plus x, which is x. Same thing for acetate. So when we write the Ka, 1.8 times 10 to the power of -5 equals to proton concentration times acetate concentration, so x times x, divided by 1 minus x. So since x is much smaller than 1, we consider it as 1, and then we cross multiply to find x. So x squared will be approximately 1.8 times 10 to the power of -5. So x will be 4.2 times 10 to the power of -3. So this is going to be the concentration of proton. So concentration of proton, which is dissociated, divided by the initial concentration of acid, will be 4.2 times 10 to the power of -3 divided by 1 multiplied by 100%. That's going to be 0.42%. So it means that only 0.42% of the original acid only dissociates. So this is a similar problem, except in this case, for the second part, you remember we had two different concentrations of the same acid, 1 mole per liter and 0.1 mole per liter. So if we use the same thing, it's going to be x squared divided by 0.1 equals to 1.8 times 10 to the power of -5. So x in this case will be, or proton is going to be 1.3 times 10 to the power of -3 mole per liter divided by 0.1 multiplied by 100% is going to be 1.3%. So as you see here, it not only depends on the type of acid, it also depends on the concentration of acids. So in the previous example, we had 1 mole per liter, so we had 0.42% dissociation. On the second part, we have 0.1 mole per liter, and we had 1.3% dissociation. Sometimes we need to find pKa from percent dissociation. For example, we have an example here calculating Ka from percent dissociation. Lactic acid or HC3 H5O3 is a waste product that accumulates in muscle tissue during exercise, leading to pain and a feeling of fatigue. In a 0.1 mole per liter aqueous solution, lactic acid is 3.7% dissociated. Calculate the Ka for this acid. So it's dissociated for 3.7%, and we have the initial concentration of this acid, which is lactic acid, which is 0.1. So what we need to write? We need to write the chemical equation. HC3H5O3 gives us proton plus C3H5O3 minus. So Ka will be like that. So we have one side initial concentration, the other side we have equilibrium concentration. Initial concentration we have 0.1 and zeros for the products, and for equilibrium we have 0.1 minus X and X for the products. So based on percent dissociation, we have 3.7% X divided by initial concentration of acid. So X will be 3.7 times 10 to the power of negative 3. So Ka will be 3.7 times 10 to the power of negative 3 multiplied by the same thing divided by 0.1. So that's going to be 1.4 times 10 to the power of negative 4. That's going to be the Ka for lactic acid. I hope you enjoyed this video. If you found it useful, please like this video. You can also subscribe this channel to find lots of videos regarding chemistry and topics in math. If you have any question, please leave me a comment and I get back to you as soon as possible. Thank you for watching and have a great day.